Hello everybody. Good afternoon guys. Hello everybody. How are you guys doing? Let me know in the chat box guys. How are you doing? How are you guys? Can you hear me and see me? All good, all okay at your end? Hello everybody. Good afternoon. My name is Shubhang and welcome to today's session on most important reactions of organic chemistry for JEE Advanced 2023. How are you guys? All good? Let me know in the chat box quickly. All good, all okay? Hello Shushant, hi Shreya, hi Janvi, hi Akhil. How are you guys? So, what are we going to do in today's session? In today's session, we are going to talk in brief about lot of reactions. What are the important points that you should keep in mind in those reactions with respect to JEE Advanced 2023? Guys, although JEE Advanced does not have a fixed pattern, does not have a fixed topic distribution or fixed weightages to chapter, we can see that repeatedly, whether it is SCQ, whether it is numeric, whether it is integer type, some logic related to certain reactions keeps repeating in the questions, isn't it? You also must have seen that when you have gone through JEE Advanced PYQs. Certain type of एक reaction है, let's say halogenation of alkane. So logics related to halogenation of alkane keep getting asked, whether here, whether there. Sometimes they'll ask about reactivity, sometimes they'll ask about number of isomers, sometimes they'll talk about percentage product, and so on and so forth. So we are going to discuss all these points in important reactions related to organic chemistry. Shall we begin? All ready? All pumped up? Start kare? Shall we start? Chalo, let's go ahead. So we'll go chronologically, as in we'll cover hydrocarbons first, then we'll go to alkyl, halide, and so on and so forth. We'll keep moving ahead. So very first reaction, which is very widely asked in exams, is halogenation of alkane. Remember halogenation of alkane? What was halogenation of alkane? One second. What was halogenation of alkane? Suppose we have an alkane given to us. We would react it with X2 in presence of light, and this would get converted to Rx. Now, in this reaction, halogenation of alkane, the most frequently asked question is number of total isomers formed as product. They either end up asking you geometrical isomers or they end up asking you total number of isomers. So such kind of questions ka practice is very, very, very important. And the easiest way to crack this part of the reaction, that is number of stereoisomers, is first write structural isomers. To be very specific, first write position isomers. For example, suppose we have this compound given to us, okay? There's an ethyl group attached to cyclopentane. Question is number of total isomers formed after monohalogenation. So first is write position isomers. That is, in this given compound, attach your halogen to different positions. Make sure you don't attach halogen to identical position 2 times. Meaning, the position this one and this one, they are identical, isn't it? If you talk about the ring 1, 2, 3, 4, 5, the opposite way also can be named 1 dash, 2 dash, 3 dash, 4 dash, 5 dash. So as you can see, positions 2 and 5 are identical. Similarly, positions 3 and 4 are also identical. Okay, so the very first step is identifying the identical positions in your given compound so that you don't add halogens twice to that position. Now we start adding halogen one position at a time. So outside the ring I can add halogen here. Again outside the ring I can add halogen here. Now let's start coming in the ring. 1, 2, and 3. Do you understand these structural isomers? So these are based on different positions of halogen attached in the given compound. How many did we get? We got 1, 2, 3, 4 and 5. Now in each case we want to comment on optical isomer. Number of chiral centers. Remember what was the formula for total number of optical isomers? 2 की power number of chiral centers. Right? So in compound number 1, do you see any chiral center? I don't see any carbon with 4 different groups attached to it. This position is not a chiral center. This position is not a chiral center. Why? Because there are 2 identical groups attached. This is identical to this. So compound number 1 has no chiral centers. Moving to compound number 2. In compound number 2, there is a chiral center here. We see 4 different groups attached. In compound number 3, there is again no chiral center. This is not a chiral position. In compound number 4, now this is a chiral center and this is also a chiral center. Please check. This group is different from this group. So you have a chiral center here. Similarly, the carbon on which halogen is attached is also chiral center. So 2 की power 2 is your answer. यहाँ पे you have 2 की power 1. In the fifth case, again we see there are 2 chiral centers. So 2 की power 2. So what's your answer? 2 की power 2 plus 2 की power 2 plus 2 plus 1 plus 1. That's 4 plus 4, 8, 8 plus 2, 10, 10 plus 2, 12. So 12 is the total number of isomers here. Got it? Now, you make a mistake in this one. What mistake do you make? You first check geometrical isomers here. Then you say that both the groups can show geometrical isomers. So both can be above, one can be above, one can be below. And then you say that every geometrical isomer has 2 chiral centers. That's a wrong logic. You are double counting it. So whenever you have groups attached in the ring, what you have to do, guys, you have to simply count the number of chiral centers. 2 की power number of chiral centers is the answer. Is this one understood? How to find number of isomers? I hope you would not discuss random things on the chat box and concentrate in the class. Now, next part, reactivity order. The other important thing that is asked in halogenation is the order of reactivity. Whose order of reactivity? One is of halogens. F2 greater than Cl2 greater than Br2 greater than I2. This is your reactivity order for halogens. What is the reactivity order for hydrogen? 3 degree hydrogen greater than 2 degree greater than 1 degree. Why? Based on stability of free radical. Next, reactivity versus selectivity. Here, if you remember, the reactivity of 3 degree, 2 degree, 1 degree for chlorine, for halogenation using chlorine was 1:3.8:4.5. If we do the same thing for bromine, we would get 1:82:1600. What does this mean? This means that for bromination, if there is a 3 degree hydrogen present, it is the 3 degree one which will get always substituted first. But if you talk about chlorination, these numbers are very close. So if there are 2 degree and 3 degree both present, we have to actually compare and check. We have to calculate and check. Got it? Now, major product identification. This is related to your reactivity versus selectivity. For example, if I give you such a case and I ask you chlorination में what will be the major product here? Chlorination में what will be the major product here? So if you check, this is 1 degree, this is 1 degree, this is 1 degree, this is 2 degree, this is 3 degree. You have 9 1 degree hydrogen, 9 with the reactivity 1. You have 2 2 degree hydrogen, 2 into 3.8, and you have only 1 3 degree hydrogen with 4.5. So as you can see, 1 degree hydrogens wins. Are you understanding? Chlorination के case में 3 degree hydrogen is present, yes, but it is only 1 3 degree hydrogen with reactivity 4.5. There are 9 1 degree hydrogens with reactivity 1, so the total is 9 there. And so major product will be when we use 1 degree positions for halogenation. Is this clear? Is halogenation of alkane understood, guys? These are the major points or most important points in halogenation of alkane that we should remember. Are you with me? Are you understanding this? Let me know on chat box quickly. Come on. Also, tell me, what do you think is the next reaction? We are in hydrocarbons, remember. So what do you think is the next reaction after halogenation of alkane? Which one should we be discussing? Quick, quick, quick. Any idea, any guesses? I'm sure you can guess. Hydrocarbon chapter is on. Alkene, absolutely correct, Karthik. And next we are going to talk about reactions related to alkene. First one in this is dehydration of alcohol. What does dehydration of alcohol means? We have an alcohol, we remove water from it and we get an alkene form. This is the reaction that I'm discussing right now. Dehydration of alcohol is a hot favorite because it involves carbocation formation, it involves carbocation rearrangement, ring expansion, lot many things can come into the picture. Therefore, dehydration of alcohol is a hot favorite for JEE Advanced paper setters. So be very careful, practice lots and lots of questions. Okay, now for example, when we talk about dehydration of alcohol and carbocation formation, let's take a case. We are reacting this with H plus concentrated. That's your step 1. The product that you get, we react it with NaH in step 2 and step 3 H3O plus. Okay. First step, H plus concentrated, a compound is given to us, we get the product. That product we react with strong base NaH, and then in the next step we react it with H3O plus. So first step is fairly simple, right? What happens in the first step? In the first step we make carbocation. One by one we make carbocation, but in the interest of time I am making all three together. Then what happens to these carbocation? They can rearrange if they want to, right? So these carbocations then enter the ring. One by one each carbocation will enter the ring, not together. Next step, because we were doing H plus concentrated, these will convert to alkene also. So we get an aromatic product formed. Now what's the next step given in the question? NaH and then H3O plus. What do you think will happen if we use NaH here? My bad guys, not H3O plus, D3O plus. So what do you think is going to happen when we use basic, very strong base with this compound in D3O plus medium? If you use very strong base with this compound, your carbon will lose an H plus, it will convert to anion, and then this anion will react with D3O plus. So your hydrogen on the group will basically get substituted with deuterium. The question is, will I get this product? All the hydrogens, will they get substituted with deuterium, or it will be only one hydrogen per carbon? What will be the answer? Will we get all the hydrogens on these carbons substituted with deuterium, or it will be a specific one only? What will be the answer? Please notice we are adding NaH in the second step and then we are adding D3O plus in the third step. It's not that I'm continuously adding NaH D3O plus, NaH D3O plus, no. So only and only one single carbon ion will be formed. Only and only one single carbon ion will be formed, and only this will give you your major product. Only one substitution, not all. So this was a simple example related to carbocation rearrangement or carbocation formation. In general, when we use H3O plus H2SO4 strong acids, then we see carbocation formation happening. Sedzeff versus Hoffman alkene. What do you mean by Sedzeff alkene? Sedzeff alkene is more stable alkene. Whenever carbocation is formed, it gets enough time to form a stable alkene as a product, or I can say when a carbocation is formed, it gives a more stable alkene as a product, which is your elimination step. Now, can we get Hoffman alkene also? Yes. Does carbocation always form? No. So, when you use dehydrating agents like THO2 or Al2O3, metal based or solid based dehydrating agents, then we do not get carbocation formed, then we do not get Sedzeff alkene, we get Hoffman alkene as a product. Very, very, very important point here. Whenever we talk about THO2, Al2O3 along with high temperature being used as dehydrating agent, no carbocation is formed as well as no rearrangement takes place, and we get Hoffman alkene as the major product. Siddharth bro, you might want to use the time to do something productive and not just waste your time and others' time on the chat box. Next, stereochemistry of product obtained. What do you mean by this now? In the dehydration of carbocation reactions, dehydration of alcohol, you get a carbocation formed and then you get alkene formed. This alkene can show geometrical isomerism. Hoffman means lesser stable alkene, correct. Sedzeff means more stable alkene. In general, Sedzeff alkenes are said to be more substituted. Hoffman alkenes are said to be lesser substituted. But correct way is Sedzeff more stable, Hoffman lesser stable. What I was telling you here is alkene is formed as a final product. When we make Sedzeff alkene, we always check hyperconjugation, resonance. We all remember all that point. What we end up not remembering is cis versus trans. It will, majority of the time it will be the case that you have trans as a major product and not cis, because that is the more stable alkene. That is what I mean, stereochemistry of the product should be taken care of. Is this understood? Carbocation formation, please one time ask. I'll take one more example if that is what you're saying. One second, how do you erase it? It is all in one slide. Let's take one more example. So this we are reacting with concentrated H2SO4, H plus heat. First step will be what? First step will be your carbocation formation. Now next step will be carbocation rearrangement. If we can make this carbocation more stable, it can rearrange. So let's rearrange and see if we can get a more stable carbocation. If we rearrange it to the right, it comes in resonance with the benzene ring. So we can definitely make this carbocation, isn't it? Now, when you form alkene out of it, we have to form ZF alkene, that is more substituted alkene, more stable alkene. So this is your compound. Is this the answer? This is not the answer. No. Why is this not the answer? Because we have put two bulky groups on the same side. That will be a lesser stable situation. Na? We have put two bulky groups on the same side. That's a lesser stable situation. I'm not saying compound is unstable. I'm saying it's a lesser stable situation. So I would want to put it this way, such that the two benzene rings, which are big in nature, are away from each other. Clear? Let's move ahead. So this was about dehydration of alcohol. Say, how do we get alkene? Next is alkyl halide se alkene. We know that when you have an alkyl halide and you react it with alcoholic KOH or NaNH2 can also be used. That's a very strong base. Alcoholic KOH is also a strong base. What do we obtain? We obtain alkene as the product. Elimination takes place. Now, we have to be very careful about certain points in elimination, guys. One is whether the reaction is undergoing E2 or E1. When do you get E1 elimination? When carbocation formed is very stable, that is 3 degree alkyl halide. In this situation, we get carbocation formed very stable. There is lot of bulkiness around the carbon carrying the halogen. So we get E1 elimination in such cases, that is a carbocation gets formed. And then elimination takes place, we get alkene as your major product. Which alkene is formed again as a major product here? ZF alkene. Whether it is E2 elimination, whether it is E1 elimination, we always get ZF alkene as the major product. Except for very specific, very certain cases. I'll give you an example. Now, here as you can see, what do we have? We have a 2 degree carbon which is carrying the halogen. It is next to a 3 degree it is next to 1, 2, 3, 4 a 3 degree position. Yeah, it is next to a 3 degree carbon. If I react this with alcoholic KOH, what do you think will happen? E2 or E1? Tell me on the chat box quickly. If I react this system, the carbon which is carrying the halogen is at 2 degree, but it is next to 3 degree. What do you think happens here? E2 or E1? E1 takes place here. E1 takes place here. Whenever you have a carbon next to a 3 degree position, it ends up undergoing E1 elimination. So what happens? You get C plus, you get CH3. Then rearrange, sorry, I'll write it here. Then rearrangement takes place. CH3, CH3, positive CH, CH3, CH2, CH3, and then you get the product. Positions next to 3 degree convert the reaction from E2 to E1. Why? Because this carbocation gets formed. Eventually alkene that will be formed will be also very stable. So alkene stability is driving this reaction. Because it's a sterically crowded position, it did not react easily via E2. Okay, so be very careful about Setzeff-Hoffman, about E1, E2. There is no specific rule here. You have to check based on carbocation stability. Okay. Stereochemistry of product, that we have already covered when we talk about Setzeff. Next, addition reactions. Alkene undergoes what kind of addition? Electrophilic addition or nucleophilic addition? Alkenes are electron rich. So electrophilic addition is the characteristic reaction of alkenes. When we add an electrophile on a given alkene, Suppose this was your alkene, we add an electrophile. This is your rate determining step. And what do we land up? We land up with this carbocation because it is more stable carbocation, right? So alkene पे electrophilic addition will always take place such that carbocation formed is more stable. Markovnikov rule का we have to remember. Markovnikov rule का we have to remember with this logic that it means carbocation form should be more stable. Don't remember it with the logic कि carbocation form should be more substituted. More stable is the correct one. That will give you right answers. So when we add an electrophile, carbocation does form. Carbocation formed such that more stable carbocation we get as a product. And then if rearrangement is possible, rearrangement does take place. Suppose here we have a benzene ring. That means here we have a benzene ring. So in this particular case, rearrangement will take place to make the carbocation more stable, to make it resonate with benzene. And then nucleophile will simply go and attach to the positive charge. This is a simple case. This is easy enough. Carbocation can be formed here as well as here. Let me call it 1 and 2. Where will it be formed? It will be formed on the first position. Why? Because it has more alpha hydrogen. 2 alpha hydrogen here. 2 alpha hydrogen, that's 4. If you form the other side pe product, you get only 2 alpha hydrogen from here. So this will be formed, not this. Okay, so we have to be very careful when we add reagents to alkenes. Okay, we have to be very careful about carbocation formed. It should be more stable. We have to be careful about how we rearrange it, and then finally we attach nucleophile to it. Now, when do we talk about anti-Markovnikov addition? Can you give me an example? Anti-Markovnikov addition on alkene. Quick. Anti-Markovnikov addition on alkene. Any example? Which reagent में anti-Markovnikov addition takes place? Kharash effect. HBr, H2O2. Anti-Markovnikov addition ka we have to remember one very specific reagent. That's hydrogen bromide or hydrobromic acid along with a peroxide initiator. Not hydroboration, oxidation. HBr plus H2O2. So this gives you anti-Markovnikov addition. No carbocation is formed. No rearrangement takes place. Nothing. Now, stereochemistry of product involved. When we add any electrophile to an alkene, we get a carbocation like this. Carbocation can be attacked from above as well as below. Therefore, when a nucleophile attaches to this position and it ends up creating a chiral center, we will get both R as well as S configuration for that chiral center. Is this much understood? Because this carbocation is planar, it can be attacked from above as well as below, and therefore what do we see? We see a chiral center being formed, 4 different groups attached, but the chiral center is formed in both options, that is plus as well as minus, R as well as S, dextro as well as levo rotation. Now, in the very first step when you attach electrophile, if that is also coming as a chiral center, that will also come in pair plus minus. Alkene is also planar in nature. So electrophile can be attached from alkene from the top or the below or the bottom. So in the first step also, when we attach electrophile, we have to be careful. If it's a chiral center being formed, it will be formed as racemic. Here in this step, when nucleophile gets attached, there also if a chiral center is formed, it will be formed as racemic. Is this much understood? Is it clear? Even E2 wala, let's take an example after we complete this slide. Last but not the least, 1,4 addition. Very important, very tricky part that they ask from here. Suppose if you have 1,3-butadiene and you react it with HBr, then what is going to be the product? Will only one alkene react or will both the alkene react? The answer depends on temperature. When 0 degrees Celsius or even lower temperatures are given, then 1,2 addition takes place. Only one pi bond pair HBr gets added. But if we give room temperature or heat, then 1,4 addition takes place. You will have hydrogen attached in the one end, bromine attached on the other. So be very, very, very careful about 1,4 addition in alkenes, guys. Be very careful about stereochemistry of product in alkenes. ठीक, चलो let's go back. कहाँ गए? यहाँ पे थे ना हम E1 E2 पे. Let's take one more example. E1 elimination or E2 elimination. This is halogen, okay? This is halogen. Compound given here, E1 elimination, E2 elimination. Quick. This undergoes E1 elimination. Why does this undergo E1 elimination? Because the carbocation formed here is very, very stable with ethyl cyclopropyl carbocation. Dancing resonance, remember? So therefore, this again will undergo E1 elimination. Why? Because the carbocation formed is very, very, very stable. What is the product expected? The product expected is this. Can we not get alkene in the ring? Can we not make this product? No. 3-member ring is already very strained, right? Very unstable or less stable. If you put sp2 carbon in the ring, it becomes more unstable, more strained. Therefore, we get this as the major product. Cool. Let's go ahead. So, alkene में the last part or hydrocarbon में the last part, very, very, very important part from matrix match perspective, from multiple correct type question perspective, oxidation of alkenes. So, alkenes can be oxidized into various products depending on the reagent used. Alkene to alkyne, how do we convert? We know that alkyne pe when you add hydrogen, you get alkene. But alkene se how do we remove hydrogen to get alkyne? We end up using an indirect method for this. We end up using an indirect method for this. Bromine in CCl4. So you get 2 bromines attached. Now you use alcoholic KOH in the first step, NaNH2 in the second step. That means we are removing 2 moles of HBr. So when you remove 2 moles of HBr, you will get your alkyne. So alkene to alkyne direct conversion is not possible. Lindlar catalyst is for addition on alkyne to get alkene. Alkene to alkyne directly is not possible. We follow indirect methods. So first important oxidation, alkene to alkyne. Second, alkene to alcohol. That was basically covered in the previous step, in the previous reaction, addition on an alkene. When you have an alkene, asymmetric alkene particularly, and you react it with any dilute acid, it ends up giving Markovnikov addition. More stable carbocation is formed. If it can rearrange, it will rearrange and water gets added. Next, alkene to diol. Any idea? Do you remember the reagent, how we convert alkene to diol? याद करो, cis diol, trans diol. Anyone? Quick, chat box is open. Live, guys, come on, interact. What's the point otherwise? Alkene to diol, so there are 2 possibilities. If we use alkaline cold KMNO4 or we use alkaline cold OSO4 and NaHSO3. This is your first step, this is your second step, this is OR. then we get cis diol or syn diol. Both OH gets added on the same side. But in the same system, if we would have used AgO2 or CF3CO3H, peroxy acid, then we get an epoxide as a product first, which on reaction with water breaks and we get anti-added OH. KMnO4, cold alkaline KMnO4 is used here, so therefore its oxidizing power is less. If you use concentrated hot alkaline KMnO4 or concentrated hot, concentrated word nahi use karte, hot acidic KMnO4, then you get acid, you are correct, but not in this case. Cold alkaline KMnO4 dilute, no. Next, this was about alkene to diol, very important reaction. Please keep in mind where it is cis, where it is anti-addition, where it is syn addition. Alkene to carbonyl, any idea, any do you remember compounds that convert alkene to carbonyl? By the way, yahan pe there are many other options also. Huh? You can use SeO2 also, that gives you allylic OH, pi bond ke next position pe OH. Alkene to carbonyl, ozonolysis can be used easily, isn't it? Alkene pe if we use reductive ozonolysis, we get aldehyde ketones as product. So alcohol bana ke we can oxidize, that is also correct, very good. If you don't want to break the alkene, you add water and then you use mild oxidizing agent like PCC. If you want to break the alkene, use ozonolysis, reductive ozonolysis. Next, alkene to carboxylic acid. We use strong oxidizing agents, K2Cr2O7H+, KMnO4H+, hot alkaline KMnO4, or oxidative ozonolysis. Ozone with water, ozone in absence of zinc or DMS. Thick, in that case we get carboxylic acid as product. If you want to convert alkene to CO2, simply burn it with O2. Simply burn it with O2, oxidize it, combust it. I can understand organic has lot many reactions, right? And it's very, very, very easy to remember them if you have a chart. Such charts we are going to provide you after this session on our Telegram channel. So if you have not joined the Telegram channel, the link is in the description. Please join the Telegram channel. There we will give you all charts of organic chemistry, entire JEE Advanced ke all reactions ka charts on the Telegram channel after the session is over. So please do join the Telegram channel. Theek, I hope this is clear, guys. Any doubt in this? Simple hai, oxidation of alkene. Various products can be obtained using different reactions. Not too much complex mechanisms. All we have to remember is which type of product is obtained where. NaNH2 is just removing, see, in the first step you got one HBr removed. Now to remove the second HBr, we are removing NaNH, we are adding NaNH2. Removal of second HBr is difficult. We want stronger base. So instead of alcoholic KOH, we use NaNH2. Next. Now, hydrocarbon chapter is incomplete without aromatic hydrocarbons, isn't it? Aromatic hydrocarbon mein there are some reactions which are simple, there are some reactions which are complicated. Friedel-Crafts reactions are one such reactions, guys, which are on the border. They are neither difficult nor easy. Rather, I should say sometimes very simple questions comes from Friedel-Crafts and sometimes very complicated questions come from Friedel-Crafts. Let's discuss the important points. Under Friedel-Crafts, we have two options, alkylation and acylation. Alkylation takes place when you have an alkyl halide with a Lewis acid. Acylation takes place when you have acyl halide with a Lewis acid. In first situation, the alkyl group goes and attaches itself to the aromatic compound. In the second situation, the acyl group goes and attaches itself to the organic compound, aromatic compound. in which case there are chances of monoalkylation या monoacylation. In which case monoacylation and monoalkylation will be higher or will be the major product. That would be the second case. In the first scenario, Friedel-Crafts alkylation, the ring is now activated. There is a donor group attached to the ring. So this ring will get alkylated again and not the reactant benzene. Here your withdrawing group is attached. That means once withdrawing group is attached, ring has lesser electron density. So this cannot react further or does not react further. Got it? So that's first point of acylation versus alkylation. The second point that we have to remember is about solvents in Friedel-Crafts reaction. Friedel-Crafts reactions do not take place on deactivated rings. Friedel-Crafts reaction does not take place on benzene rings which have deactivated groups attached to them. That's aldehyde, that's ketone, acid, ester, NO2, these are cyanide, these are all strong withdrawing groups. They deactivate the ring a lot and Friedel-Crafts reaction does not take place. So very, very, very important point to remember. Next, rearrangement conditions. In this first case, what is formed actually, suppose I take Lewis acid as AlCl3, then actually speaking, this is the compound that is first formed. There's a del plus here, there's a del minus here. This is the compound that is first formed, a complex, an activated complex formed using Lewis acid and Rx. If enough temperature is available, if the correct Lewis acids are used, only and only then this gives you carbocation. So if heat is given or room temperature is given, then we definitely make a carbocation. If heat or room temperature is not given or low temperature is mentioned, then we do not make carbocation, no rearrangement. Is this much understood? This also depends on which Lewis acids you are using. Last case, preferential attack on the ring. What does this mean? Suppose you have this compound on which you are using Friedel-Crafts. Then the question is, on which position will alkyl group go and attach itself? So as you know, this is your plus H group. It donates electrons. On which positions? Ortho and para position. But this is also a plus I group. It gives ortho position pe more pushing of electrons. So therefore your Friedel-Crafts alkylation takes place at one of the ortho positions. This is what I meant, preferential attack on the ring. These are some very important points in Friedel-Crafts reactions. Please make sure you remember them. Okay, let's quickly move ahead. Otherwise, we'll not be able to complete the session. Next, I have discussed a lot about SN1, SN2, SN-NGP, SNI in the reaction mechanism videos. If you'll go on the channel, if you'll check the previous videos posted by me, 2 sessions I had taken on reaction mechanism question solving, where we talked in depth about these 3. When to do SN1, what to do in SN1, when to do SN2, what to do in SN2, when to go for SNI, that is intramolecular, and when not to go for SNI. What we did not discuss there was SN-NGP. So right now I'll concentrate on SN-NGP itself. Cool. So let's start. SN-NGP means what? Substitution nucleophilic by neighboring group participation. Substitution nucleophilic by neighboring group participation. Let me take a standard example of this. This is your compound and I am reacting it with a nucleophile for substitution. The second case is your compound where halogen and OCH3 are on the same side. And we use nucleophile. Question is, what is the product in each situation? SNAR in alkyl halide? No, that comes in aryl halide. So I'm not talking about SNAR right now. Now, nucleophilic attack has to take place, but if you notice, the compound has a nucleophile of its own. This X is your leaving group, but the compound has a nucleophile of its own as well. Here also. Always internal attacks are faster than external attack. Internal attack in the molecule, if there's a group in the molecule, it will attack inside the molecule faster. So, yahan se attack takes place, this halogen goes away. When the attack takes place and halogen goes away, what do we get? We get OCH3 like this. And then who will attack? Nucleophile attacks. OCH3 goes back. We get retained product here. Because there are two SN2 steps involved in SNNGP. This is your first SN2 step where inversion took place. This is your second SN2 step where again inversion took place. So 2 times inversion means retention. So the important point in SNNGP and SNI is retention of configuration. SN2 may be studied that configuration is inverted. SNI may be studied racemization takes place with slightly excess inverted product, but SNNGP and SNI may retention happens. In this first situation, this OCH3 cannot attack the carbon carrying halogen. They both are on the same side. No matter, sorry, when we conduct SN2 step, see, individually this was also SN2 step, individually this was also SN2 step. So this is also, if this attack takes place, this will also be an SN2 step. SN2 is always a backside attack, not a front side attack. SN2 is always backside attack, not front side attack. So this reaction cannot take place. Understood about SNNGP, guys? For SN1, SN2, SNI, please go and watch the previous video, reaction mechanisms. They have been discussed in 2 parts. Stereochemistry of product obtained. What do you think happens in SN1? In SN1, a carbocation is formed, yes, but it's a planar carbocation. So it can be attacked from above as well as below. So we get racemized product when SN1 takes place. SN1 may we get racemized product. What happens in SN2? SN2 may we get inverted product. But no reaction can be pure SN1 or pure SN2. All reactions may SN1, SN2 happen together. It all depends on which is happening as the major one. So even when SN1 is taking place, there will always be some amount of SN2 happening. Okay. So in SN1, when we say racemization takes place, not 100% racemization takes place. There will always be slight amount of inversion product more. For details, please watch the first video of reaction mechanism. Next. Elimination reactions. We have already covered about E1, E2 when we were talking about alkene. When we talk about formation of alkene from alcohol, there we discussed about E1, E2. Same logics of E1, E2 are applicable here as well. When you have a 3-degree alkyl halide, one which can give stable carbocation, it will undergo E1. Otherwise, this undergoes E2. Moving ahead from this. Now, I understand there are lots of reactions throughout organic chemistry, guys, which get asked in exam, but few ones are very important. E1 CB, yes, E1 CB kar lete hain discuss. My bad, I missed it. Now, E1 CB is a competing reaction of E2. E1 CB is a competing reaction of E2. Suppose you have a compound which is given to you like this. Okay, and let's say, oh sorry, in this first case, guys, fluorine is attached. It's a poor leaving group. That does not mean it will undergo E1CB. Only when poor leaving group is attached, it does not undergo elimination unimolecular via conjugate base mechanism. It undergoes E1CB when you have a poor Lg and you have a very good electron withdrawing group. When both of these conditions are satisfied, only and only then we get E1CB as the product, or as the mechanism, sorry. What will happen in this case? In this case, you have a CHO here, you get a carb anion formed, this carbon ion comes back, halogen goes away, and you have your CHO. In this first case, simple elimination takes place via E2 mechanism, you get alkene. Whether retention or whether inversion takes place in E1CB, as you can see, a carbon ion is, first of all, E1CB is elimination. Elimination may we make ZZ for Hoffman alkene. In this case, the eliminated product, the alkene formed, depends on where the carbon ion is more stable. Whichever place pe you have your electron withdrawing group, on that carbon your carbon ion will be more stable. That will decide the alkene. Understood, Tarun? Elimination may we don't talk about retention or inversion. We talk about Hoffman or Setzef alkene formed as a product. And wherever the carbon ion is more stable, that means where EWG is present, that place decides your alkene formation. Next. Last 2-3 reactions we have to cover now from carbonyl chapter. Very, very, very important reactions. They get asked in various forms. The logic gets asked a lot. One such reaction is aldol reaction. These are the variations or important points that we have to remember in aldol. If you remember, base catalyzed aldol mechanism mein what is formed as an intermediate? Enolate ion is formed as an intermediate. Enolate ion ki basicity decides. Enolate ion ki basicity decides the direction from which we start aldol. Meaning, if I have this compound and I react it with OH minus, which is your more acidic site, the left or the right? The most acidic site is this one, the left one, because it is lesser substituted. So that is where the reaction starts from. You get enolate, sorry, you get enolate form. The enolate attacks on your carbonyl and you get addition reaction taking place on the carbonyl. 1, 2, this was the carbonyl which got attacked, O minus in carbon. ठीक है? So basic mechanism में acidity of the alpha position, acidity of the alpha carbon decides who will attack. Overall aldol की condition or compulsory condition for occurrence of aldol is presence of alpha hydrogen on a carbonyl compound. Now acid catalyzed mechanism discuss करते. What do you mean by acid catalyzed mechanism? Acid is used for conducting the reaction. In acidic medium, first enol gets formed, not enolate ion, enol gets formed. Okay, so the side which has more stable enol, that side initiates the reaction. The side which will give more stable enol, that side initiates the reaction. So in the given compound, this is your more stable enol. So the reaction now takes place from this end, the right end, not the left end. Is this point clear to everybody, guys? The reaction takes place from the right end, not the left end. Left end was in basic medium where acidity is to be checked. In acidic medium, alkene stability or enol stability has to be checked, so it will take place from the right. Now, these are various examples of aldol. We should be very careful. Self-aldol is what I taught you here or what I discussed here. Compound reacting with itself. Cross-aldol is where you have two compounds reacting with each other. Suppose I have acetone reacting with acetaldehyde. Acetone reacting with acetaldehyde without considering geometrical or optical isomerism, stereoisomerism. Tell me how many different products can be obtained. Without considering geometrical isomerism, tell me how many products can be obtained. So if I say this as compound A, this as compound B, so compound A can attack on A, compound A can attack on B, B can attack on A, or B can attack itself. So 4 different products get formed without considering stereoisomerism. If you consider stereoisomerism, maybe more products get formed. So cross Aldol pay questions are generally asked in multiple correct type, where they want you to tell what are the different products obtained in the reaction. ठीक? Reverse Aldol. Aldol reactions are highly reversible in nature if you use higher concentration of base. If you use higher concentration of base or higher concentration of acid, then reverse reactions are possible. Your reactant gets regained again. It's a very difficult reaction to digest. It's very difficult reaction to detect in exam that what is he wanting me to do. He will give you this compound as a product and he will say reaction of this with strong base gives. So it's called reverse Aldol or retro Aldol, that we should remember nicely. Cyanoaldol and nitroaldol kahan gaya? I missed nitroaldol. Okay. Cyanoaldol and nitroaldol. Just like aldehyde ka alpha position or carbonyl ke alpha position se we are taking away the alpha hydrogen, forming enolate. Similarly, cyanide and NO2 are also strong withdrawing groups. Unke alpha position se we can also form anion and take the reaction ahead. So cyano and nitroaldol are a variation of your simple aldol. These are not on carbonyls, these are on cyanide and nitro containing compounds. Intramolecular aldol. If your compound has 2 carbonyl positions, if your compound has 2 carbonyl positions, let's say this here and this here, so such a compound can undergo intramolecular aldol. That is, cyclization will take place in the molecule. In intramolecular aldol, we have to be very careful of the product formed. Product cannot be unstable. We cannot make 4-member or 7-member rings. We have to preferably make 5-member or 6-member ring. In this case, 1, 2, 3, 4, 5, 6. That means this much part can form 6-member ring. So first position attacks the 6th position, closes the ring. Or you can say 7th attack the 2nd, same thing. Thick. Last, Claisen-Schmidt. Claisen-Schmidt reaction is a variation of aldol. It is not in carbonyls, it is rather in esters. Same mechanism, identical thing that we did here. In basic medium, first we made anion, then the anion attacked the carbonyl. Same way you take ester in basic medium, ester ke alpha position pe you get anion, it attacks a given carbonyl or another ester and reaction takes place ahead. Okay? So this was a gist about aldol reaction. Next. Cannizzaro. Cannizzaro reactions are reactions of carbonyl compounds without alpha hydrogen. Cannizzaro reaction are reactions of carbonyl compound without alpha hydrogen. This is essentially a disproportionation reaction. If you talk about, let's say, formaldehyde undergoing Cannizzaro reaction, this one compound will get oxidized, the other will get reduced. So Cannizzaro reaction is essentially a disproportionation reaction. Cannizzaro pe important questions come from cross Cannizzaro. Okay? For example, you have HCHO and you have PHCHO. So who gets reduced, who gets oxidized? It's always the compound which has higher del plus, the one gets oxidized. The compound which has higher del plus always gets oxidized. Compound which has lesser del plus gets reduced. This is a very simple way to identify in cross aldol which gets oxidized, which gets reduced. Is this much clear? In cross aldol, it is very important to identify correct oxidation product, correct reduction product. The carbonyl which has high del plus always gets oxidized. The carbonyl which has lower del plus gets reduced. Reactions like Cannizzaro, benzyl benzylic acid rearrangement, benzyl benzylic acid type rearrangement, where you don't have this hydrogen which is migrating, but there is an alkyl group which migrates. So there are very specific cases in which alkyl group can also migrate. Let me take the example of retroaldol now, and then we'll wrap up the session perhaps. So this is your compound given to you, okay? And the question is, if I react this with OH minus water, what is the product obtained? It's very difficult to guess that we are talking about retroaldol. It's very difficult to guess that we are talking about retroaldol here. How do we guess that कि retroaldol के बारे में बात हो रही है? One is that basic medium is given. That is an identifier. Second is it is alpha beta unsaturated carbonyl. Alpha beta unsaturated carbonyl along with basic medium is the idea to conduct retroaldol. What is the product of retroaldol? You simply break it from here. Where carbonyl is present, don't give carbonyl there. Where carbonyl is present, don't give carbonyl there. Give hydrogens. Where carbonyl is not present, you give carbonyl there. This is the shortcut that you do in aldol as well, right? Alpha position se we remove 2 hydrogen and oxygen, so we get product. Similarly, product may be added water, we got your reactant. Got it? So this was it, guys. We discussed lot many reactions of organic chemistry. We will provide you beautiful charts of all the compounds related, of all the systems related to organic chemistry for JEE Advanced on our Telegram channel after the class. So please join the Telegram channel and stay tuned for many such wonderful videos and learning sessions coming up your way till JEE Advanced. Thank you so much, guys, for joining. Take care. Bye-bye. Bye, guys.